Right now, space itself is carrying 97% of the observable universe beyond the reach of humanity forever. Not in billions of years. Right now, this is not about speed limits or fuel problems or technology that does not exist yet. This is about the fabric of reality stretching faster than anything can travel through it. Scientists confirmed this decades ago, and the implications shatter every dream of intergalactic civilization. The universe is not just expanding, it is accelerating. No warp drive, no wormhole, no physics we might ever discover can overcome what cosmological expansion has already done. If these kinds of cosmic journeys fascinate you, and you enjoy understanding the true boundaries of human existence, tap that like button and subscribe. Now, get yourself nice and comfortable. Let's begin. Edwin Hubble changed everything in 1929. Standing at the eyepiece of the 100-inch Hooker telescope on Mount Wilson, peering through the crisp California night air, he noticed something that would rewrite humanity's understanding of cosmic distances forever. Galaxies were running away from us. Every single one of them, and the farther they sat from Earth, the faster they fled. This was not random motion through space. This was something far stranger. Space itself was stretching, carrying galaxies along for the ride, like raisins embedded in rising bread dough. Before Hubble's discovery, astronomers believed the universe was static and eternal. Stars and nebulae occupied fixed positions in a celestial framework that had persisted since creation itself. This view dominated scientific thinking for centuries, embedded so deeply in cosmological assumptions that even the greatest minds of the era refused to consider alternatives. The universe had always existed and would always exist in essentially its current form. This was not merely scientific consensus. It was philosophical bedrock. Albert Einstein, whose general theory of relativity revolutionized physics in 1915, initially resisted the implications of his own equations, which suggested the universe should be expanding or contracting. He introduced a cosmological constant to force his mathematics to describe a static cosmos, a modification he later called his greatest blunder. Other physicists, including Alexander Friedmann and Georges Lemay, recognized the expanding universe their equations predicted before observations confirmed it. Hubble demolished the static universe with careful observations of what were then called spiral nebulae. Using Cepheid variable stars as cosmic distance markers, he proved these fuzzy patches of light were not clouds within our Milky Way, but entire galaxies lying millions of light-years beyond our cosmic neighborhood. This discovery alone would have secured his place in scientific history. But his next observation changed everything. Hubble noticed that light from these distant galaxies was systematically shifted toward redder wavelengths. This redshift revealed motion. When a light source moves away from an observer, the wavelengths of its light stretch longer, shifting toward the red end of the spectrum. The same principle explains why an ambulance siren drops in pitch as it races away from you. Sound waves stretch as the source recedes, lowering the frequency. Light waves behave identically. Hubble found that virtually every galaxy he observed showed this telltale redshift. They were all receding from Earth, but the truly revolutionary insight came when Hubble plotted galaxy distances against their recession velocities. The relationship was linear and unmistakable. Galaxies twice as far away receded twice as fast. Galaxies 10 times more distant fled at 10 times the velocity. This precise mathematical relationship could not result from random galactic motions. If galaxies were simply flying through space in random directions, some would approach while others receded. The velocities would show no correlation with distance. Instead, Hubble found perfect proportionality. Something fundamental was happening to the fabric of space itself. The mathematics Hubble derived from his observations became known as the Hubble constant. This number describes how fast the universe expands at different distances, currently measured at approximately 70 kilometers per second per megaparsec. This constant tells us that for every 3.3 million light-years of distance between us and another galaxy, that galaxy recedes from us at an additional 70 kilometers per second. The measurement itself required decades of refinement. Early estimates varied wildly, with some calculations suggesting the universe was younger than the oldest stars it contained. This obvious impossibility indicated systematic errors in the measurements. Determining accurate distances to remote galaxies proved extraordinarily difficult. Different methods gave different answers. Calibration errors propagated through calculations. The scientific community debated the true value of the Hubble constant for generations. Modern instruments, including the Hubble Space Telescope, appropriately named for its pioneering discoverer, have narrowed the value to remarkable precision. The Planck satellite's observations of the cosmic microwave background provide independent confirmation. Ground-based surveys, mapping millions of galaxies, offer yet another measurement method. Multiple approaches converge on similar values, building confidence that we understand this fundamental cosmic parameter. The current best estimate places the Hubble constant at approximately 70 kilometers per second per megaparsec. Though slight tensions between different measurement methods continue generating scientific discussion, at first glance, 70 kilometers per second seems manageable. Spacecraft have achieved higher velocities leaving our solar system. The Voyager probes travel at roughly 17 kilometers per second relative to the Sun. The Parker Solar Probe has reached speeds exceeding 190 kilometers per second during its closest approaches to our star. New Horizons cruised past Pluto at approximately 14 kilometers per second. Surely advanced technology could overcome recession velocities of mere tens of kilometers per second. But the insidious nature of cosmic expansion reveals itself when you multiply that recession velocity across billions of light-years. Consider specific examples to grasp this scale. The Virgo cluster, a massive concentration of over 1,300 galaxies, lies approximately 54 million light-years from Earth. At this distance, cosmic expansion carries Virgo away at roughly 1,200 kilometers per second. This velocity exceeds anything human technology has achieved, but it remains conceivably within reach of advanced propulsion systems that physicists have seriously proposed. Look further, and the numbers grow terrifying. The Coma cluster sits 320 million light-years distant. Its recession velocity exceeds 7,000 kilometers per second. The Perseus cluster at 240 million light-years recedes at approximately 5,300 kilometers per second. The Shapley supercluster, one of the most massive structures in the observable universe, lies 650 million light-years away and recedes at nearly 15,000 kilometers per second. At a distance of approximately 3 billion light-years, galaxies recede at 70,000 kilometers per second. This represents nearly 1/4 the speed of light. At 10 billion light-years, recession velocities approach 230,000 kilometers per second, more than 3/4 of light speed. The relationship is linear and merciless. Double the distance and you double the recession speed. No exceptions, no loopholes, no mercy for human ambition. Consider the galaxy GNZ 11, one of the most distant objects ever observed. When we see it, we observe light that departed approximately 13.4 billion years ago, when the universe was only about 400 million years old. At that time, GNZ 11 sat relatively close to the region of space that would eventually contain our Milky Way. But during those 13 billion years of light travel, expansion carried GNZ 11 far across the cosmos. Today, this ancient galaxy lies approximately 32 billion light-years distant, far beyond the cosmic event horizon. We see its ancient image, but its current location is permanently unreachable. At a distance of approximately 14 billion light-years, the math reaches a critical threshold. Galaxies at this distance recede at 300,000 kilometers per second. This number should sound familiar. It is the speed of light, the absolute cosmic speed limit that nothing can exceed through local space. At 14 billion light-years, cosmic expansion carries galaxies away from us at precisely the velocity that light travels toward us. But here is where human intuition begins failing catastrophically. This recession velocity has nothing to do with galaxies moving through space. Distant galaxies are not rocketing away from us like spacecraft fleeing a launch pad. They are mostly stationary relative to local space. An observer standing on a planet in one of these distant galaxies would see nearby stars hanging motionless in their sky, just as we see our stellar neighbours holding steady positions in ours. Local physics works identically everywhere. Stars orbit galactic centres at normal velocities. Planets circle stars at expected speeds. Nothing unusual happens in local space. The space between us and those distant galaxies is stretching, creating new distance faster than anything could travel across it. This is not motion. This is expansion. The distinction sounds subtle but carries universe-shaping consequences that determine the ultimate boundaries of human existence. Imagine two ants standing on a rubber band. The ants are not walking. They are perfectly still, frozen in place, making no effort to move. But someone is stretching the rubber band from both ends. Despite neither ant taking a single step, they move apart. Not because they are travelling, but because new rubber appears between them. The rubber band itself grows longer, carrying the ants along as passive passengers. Neither ant experiences any sense of motion. Neither ant feels acceleration. From each ant's perspective, it remains stationary, while its companion recedes. Cosmic expansion works identically. New space is constantly being created everywhere in the universe. Not at the edges, not in some special location, not radiating outward from a central point. Everywhere simultaneously. Between every galaxy and its neighbours. Between every cluster and its surroundings. Between every supercluster and the cosmic web surrounding it. Even within galaxies themselves, though gravitational binding overcomes expansion at these smaller scales, galaxies embedded in this expanding space get carried apart by the stretching of the cosmic fabric itself. They are not fleeing from Earth. Earth is not special. Every galaxy sees every other galaxy receding in the same pattern. Observers in the Andromeda galaxy would see us receding from them at the same rate we see them approaching us through local motion. Observers in galaxies billions of light-years away would see their neighbours fleeing just as we see ours. The expansion is uniform and universal, affecting all of space equally. No location occupies the centre. Every location appears to be the centre from which all else recedes. This distinction between motion through space and expansion of space creates the most important boundary in cosmology. Scientists call it the Hubble sphere. This invisible surface surrounds Earth at a distance of approximately 14 billion light-years. At this precise distance, the recession velocity created by cosmic expansion exactly equals the speed of light. The Hubble sphere is not a physical barrier. You could not touch it or detect its presence with any instrument. It is a mathematical boundary defined by the relationship between expansion rate and light speed. No wall exists at this distance. No force blocks passage. The boundary emerges purely from the mathematics of expansion. Inside this sphere, expansion carries galaxies away slower than light travels. Light from these galaxies can reach us, though the journey takes billions of years. Outside this sphere, expansion wins the race. Light cannot make progress against the stretching of space. Galaxies beyond the Hubble sphere are moving away from us faster than light. This statement sounds impossible. Einstein proved that nothing can travel faster than light. Relativity represents one of the most thoroughly tested theories in physics. How can galaxies violate this fundamental law? The answer lies in the crucial distinction between motion through space and expansion of space. Einstein's speed limit applies to objects moving through local space. No rocket, no particle, no information can travel faster than 300,000 kilometers per second through the space surrounding it. This law remains inviolate. Every experiment ever conducted confirms it. Nothing in the universe violates this fundamental constraint on motion, but space itself faces no such restriction. The fabric of the cosmos can stretch at any rate without violating relativity. Expansion is not motion. No object travels anywhere. Space itself grows, and objects embedded in that space get carried along. When we say distant galaxies recede faster than light, we mean that the space between us and them grows faster than light could cross it. The galaxies themselves remain nearly stationary relative to their local surroundings. They are being carried by expanding space, not propelled through it. This loophole allows superluminal recession without violating physics. Einstein's equations of general relativity explicitly permit it. The mathematics describing cosmic expansion requires no modification to accommodate faster-than-light recession. This is not a workaround or an exception. It is how the universe fundamentally operates, and it creates the most fundamental barrier humanity will ever face. Think carefully about what this means. Light leaving a galaxy beyond the Hubble sphere right now will never reach Earth. Those photons travel toward us at 300,000 kilometers per second through local space. They make genuine progress in their immediate vicinity. Each photon moves forward relative to the space surrounding it at the maximum possible velocity. No physical law prevents their journey, no force opposes their motion, but the space they are traveling through stretches faster than they can cross it. Despite racing toward us at the cosmic speed limit, they fall further behind with every passing moment. The photons travel forward. The space they must cross grows faster than they travel. Net progress becomes impossible. Picture a swimmer trying to reach shore while a powerful current pulls them backward. The swimmer strokes forward with all their strength, making genuine progress through the water immediately surrounding them. Arms pull through liquid, legs kick against the flow. The swimmer moves forward through local water at maximum human velocity, but the current carries them away faster than they can swim. Despite continuous effort, despite never stopping, despite perfect technique, the shore recedes into the distance. The swimmer will never arrive no matter how long they keep swimming. This is not a limitation of swimming ability. It is a fundamental feature of the environment. Photons from distant galaxies face this exact predicament. They travel toward us through local space at maximum possible velocity, but the expanding universe carries them backward faster than they advance forward. These photons will travel forever without making net progress toward Earth. They are trapped on a cosmic treadmill, running at full speed while losing ground with every stride. The numbers become staggering when you calculate how much of the observable universe lies beyond this critical boundary. The observable universe extends 46.5 billion light-years in every direction. This distance represents the maximum range from which light has had time to reach us since the Big Bang. It encompasses everything humanity has ever observed or could ever observe using electromagnetic radiation. Every galaxy in every telescope image, every quasar in every survey, every photon ever detected from cosmic sources. The Hubble sphere has a radius of only 14 billion light-years. Compare these figures, and a disturbing truth emerges. Volume scales with the cube of radius, which means the Hubble sphere contains only a tiny fraction of the observable universe. More than 97% of the observable universe already lies beyond the distance where cosmic expansion exceeds light speed. The overwhelming majority of galaxies we can see in our deepest telescope images occupy regions of space that are currently receding faster than light. We see these galaxies only because their light began traveling toward us billions of years ago, when they were much closer. When those photons departed, expansion had not yet carried their source galaxies beyond the Hubble sphere. The light escaped before the door closed, but the galaxies themselves have long since crossed into superluminal recession. We observe their ancient images, while their present locations lie beyond the speed of light barrier. Consider the Hubble ultra-deep field, one of the most distant glimpses into the cosmos ever captured. This image reveals galaxies whose light departed over 13 billion years ago. When that light began its journey, those galaxies sat perhaps 1 or 2 billion light-years from our cosmic neighborhood, close enough for photons to eventually bridge the gap. The early universe was smaller, denser, more compact. Distances between structures were measured in millions or low billions of light-years, rather than the tens of billions that separate us today. But space stretched continuously during the journey. Every moment of those 13 billion years, expansion added new distance between the traveling photons and their destination. The galaxies receded as their light approached. The photons made progress through local space, while the space itself grew faster than they could traverse it. By the time Hubble captures their ancient images, those same galaxies have been carried 30 or 40 billion light-years distant. We photograph their infancy while their current locations have long since crossed beyond the Hubble sphere. But the Hubble sphere is not the final boundary. It represents where expansion currently matches light speed. The true edge of human reach lies at an even closer distance called the cosmic event horizon. This horizon marks the absolute limit of what humanity could ever influence or visit, even with unlimited time and perfect technology. The event horizon differs from the Hubble sphere in a crucial way. The Hubble sphere marks where recession velocity currently equals light speed, but light that departed from galaxies near this boundary billions of years ago, when expansion was slower, can still be reaching us now. The photons escaped before expansion accelerated to its current rate. They have been traveling toward us since eras when the cosmic speed limit was not yet exceeded at their source locations. The event horizon accounts for this temporal complexity. It marks the boundary beyond which light emitted today will never reach Earth, accounting for all future changes in expansion rate. The cosmic event horizon currently sits at approximately 16 billion light-years. Any galaxy beyond this distance is permanently and irrevocably cut off from Earth. Light signals we send today will never reach them. Spacecraft we launch tomorrow will never arrive there. No message, no probe, no physical influence of any kind can ever cross from our cosmic neighborhood into those forever inaccessible regions. This is not a technological limitation. This is a cosmological fact. The event horizon exists because space between here and there will always expand faster than anything can traverse it. Not currently faster. Always faster. Forever faster. The mathematical models that predict this horizon account for cosmic evolution across infinite future time. They project how space will stretch across billions and trillions of years. There is no waiting period, after which the barrier opens. There is no future era when conditions might change. The separation is permanent by the deepest definition of that word. This brings us back to the real boundary that cosmological expansion creates. Every technology humans might develop, every propulsion system we might imagine, every clever physics trick we might discover faces the same fundamental barrier. Expansion is not a velocity to overcome. It is the continuous creation of distance itself. You cannot fly faster than distance appearing. Consider the most optimistic scenarios for human space travel. Theoretical physicists have proposed warp drives that could move spacecraft through space at effective superluminal velocities. The Alcubierre metric describes a bubble of warped space-time that could carry a vessel faster than light, relative to distant observers, while never exceeding light speed locally. The mathematics of general relativity permits such configurations. No fundamental law explicitly forbids them, but examine why warp drives cannot solve the expansion problem. A warp drive manipulates the geometry of space-time to create effective motion. It compresses space ahead of the vessel and expands space behind it, creating a wave that the ship rides like a surfer. The bubble moves faster than light, while the ship inside remains stationary relative to local space. In principle, such a drive could reduce travel times between stars from centuries to days. Science fiction has embraced this concept as the key to interstellar civilization. However, warp drives move spacecraft through existing space. They manipulate local geometry, but do not address the continuous creation of new space that expansion produces. Consider the problem carefully. A warp bubble compresses the space ahead, but expansion simultaneously creates new space ahead. Beyond certain distances, expansion creates space faster than even a warp bubble could compress it. The drive pushes forward, expansion pushes back harder. No progress results regardless of drive power. The mathematics are unforgiving. Imagine a warp drive capable of 100 times light speed relative to the cosmic frame. This represents technology so far beyond current physics that it might as well be magic. No known principles suggest how to build such a device. The energy requirements alone would exceed the output of entire stars. Yet even this fantasy technology faces the same fundamental barrier. Galaxies receding at 1,000 times light speed due to expansion would still pull away. It is the continuous generation of new distance. Wormholes face different but equally fundamental limitations. These hypothetical tunnels through space-time could theoretically connect distant points through higher dimensional shortcuts. Enter a wormhole here. Exit at a distant galaxy instantly. The vast separation through normal space becomes irrelevant when you simply step around it. General relativity permits wormhole geometries. The mathematics works. The equations balance. But creating a wormhole requires establishing a connection between 2 points. You cannot create a shortcut to somewhere that lies beyond causal contact. The event horizon marks precisely the boundary where causal contact ends. No signal, no particle, no gravitational influence from Earth can ever reach regions beyond this boundary. You cannot build a tunnel to a location that no information about your existence can ever reach. Consider the practical requirements. To create a wormhole to a distant galaxy, you would need to somehow establish a connection to that location, perhaps by sending one mouth of the wormhole there while keeping the other mouth here. But sending anything to a location beyond the event horizon is precisely what expansion prevents. The wormhole mouth would face the same barrier as any other object. It would chase a receding destination forever without arriving. The event horizon is not a wall you can tunnel through. It is not a barrier you can circumvent with clever geometry. It is the absence of any possible causal relationship. Beyond this boundary, Earth's existence is literally unknown and forever unknowable. The laws of physics prevent any information about us from ever propagating to those regions. You cannot establish a shortcut to places that cannot know you exist. The very concept becomes incoherent. Some might argue that future physics could reveal loopholes in our current understanding. Perhaps dimensions beyond the 4 we experience might offer pathways around the expansion barrier. Scientists remain appropriately humble about the limits of current knowledge. New discoveries constantly reshape our understanding of reality. The history of physics includes numerous examples of apparently fundamental limits being circumvented through deeper understanding. But cosmological expansion is not a theory waiting for revision. It is directly observed through multiple independent methods that all point to the same conclusion. This is not a mathematical prediction, awaiting experimental confirmation. This is measured reality. Type Ia supernovae serve as cosmic distance markers, confirming expansion rates across billions of light-years. These explosions occur when white dwarf stars accumulate enough matter from companion stars to trigger runaway thermonuclear fusion. The physics governing these detonations produces remarkably uniform peak luminosity, making them ideal standard candles for measuring cosmic distances. Observations of thousands of Type Ia supernovae across cosmic history reveal the expansion rate with extraordinary precision. The data leave no room for doubt. Space is expanding at measured rates. The cosmic microwave background radiation contains imprints of expansion from when the universe was only 380,000 years old. This faint glow permeating all of space represents the oldest light in the universe, released when the cosmos first became transparent to radiation. Tiny temperature fluctuations in this radiation encode information about the early universe's composition and expansion rate. Satellites including COBE, WMAP, and Planck have mapped these fluctuations with exquisite detail. The patterns precisely match predictions of an expanding universe with specific expansion parameters. Baryon acoustic oscillations provide yet another confirmation. Sound waves propagating through the early universe left subtle imprints in the distribution of galaxies. These cosmic ripples create a characteristic pattern in galaxy clustering that serves as a standard ruler for measuring cosmic distances. Surveys mapping millions of galaxies have detected this pattern and used it to verify expansion measurements. The results agree with other methods to remarkable precision. These observations converge from completely independent lines of evidence. Different physical phenomena, different measurement techniques, different research teams, different decades of scientific effort, all pointing to the same conclusion. The expansion of space is as well established as any phenomenon in physics. It stands alongside conservation of energy, the constancy of light speed, and the laws of thermodynamics as a foundational principle of how the universe works. Every photon arriving from distant galaxies tells the same story. Space is stretching. The wavelengths of light grow longer during their billion-year journeys, shifted toward the red by the expansion they travel through. The amount of stretching reveals how much the universe expanded during each photon's voyage. Ancient light carries this information across cosmic time, confirming expansion through every observation we make, and the stretching is accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, transforms the nature of cosmic isolation. Not only is the universe expanding, but the expansion rate itself increases over time. Galaxies are not merely receding, they are receding faster every moment. The distances between cosmic structures grow at an ever-increasing pace. Galaxies beyond the cosmic event horizon will remain forever unreachable, not because our technology is primitive, but because reaching them is physically impossible in any universe governed by the laws we observe. This is not pessimism. It is not failure of imagination. It is recognition of how reality actually operates. Confirmed observations reveal that the most distant galaxies visible in our telescopes already lie beyond the cosmic event horizon. We see them only because their light began traveling toward us billions of years ago, when they were much closer. When those photons departed, expansion had not yet carried their source galaxies beyond reach. The light escaped the closing door, but the galaxies themselves have long since crossed into permanently inaccessible regions. We observe their ancient images while knowing we can never visit their current locations. This creates a profound irony at the heart of observational cosmology. The universe shows us what we can never have. Every deep field image from the Hubble or James Webb Space Telescope displays thousands of galaxies that humanity will never reach. Their light arrives as a final message from across an uncrossable gulf. By the time we see them, they are already beyond any possible contact. We receive postcards from regions that have already departed from any possible connection to Earth. Understanding this boundary requires abandoning comforting assumptions about cosmic exploration. Science fiction has trained us to imagine faster than light travel. As the ultimate challenge, achieve warp speed and the galaxy opens up. Develop hyperspace technology and intergalactic civilization becomes possible. These narratives assume the universe presents a static arena where sufficiently advanced travelers could eventually go anywhere. But cosmological expansion reveals that the real barrier is not technological. It is fundamental to the structure of space and time. The universe is not a static arena waiting for sufficiently advanced explorers. It is a dynamic system, actively creating distance faster than anything can travel. The arena itself grows during every moment of every race, adding track length faster than any runner can cover ground. Physicists describe this situation using the language of causal separation. Two regions of space are causally separated when no signal, no particle, no influence of any kind can travel between them. Events in one region cannot affect events in the other. They exist in complete isolation despite both occupying the same universe. They share cosmic history but have no cosmic future together. The concept is precise and mathematical. Causal separation is not an approximation or an engineering limitation. It is a fundamental feature of spacetime geometry. Most of the observable universe is already causally separated from Earth. The light we receive from these regions departed billions of years ago, when causal contact was still possible. Ancient photons carry information from an era when their source galaxies remained reachable. We observe the past while the present lies forever beyond our reach. This brings us back to the fundamental constraint that no technology can circumvent. Cosmological expansion does not create a barrier that clever engineering might someday breach. It creates permanent separation that is woven into the fabric of reality itself. Distant galaxies are not hiding behind walls we might eventually climb. They are not waiting in rooms we might eventually enter. They are falling into horizons that no future achievement can overcome. The numbers quantify our cosmic prison with brutal precision. Approximately 2 trillion galaxies populate the observable universe. This staggering count emerged from careful analysis of deep field images, extrapolating observed galaxy densities across the full sky. 2 trillion galaxies, each containing billions of stars, spread across the observable cosmic volume. Current estimates suggest that fewer than 100 billion of these galaxies remain even theoretically reachable. The rest have already crossed beyond the cosmic event horizon. Their stars, their planets, their potential civilizations exist in a realm that humanity can never enter. Every second that passes, more galaxies cross this threshold. Space continues stretching. The event horizon creeps closer. The fraction of the universe accessible to humanity shrinks continuously, while we remain unaware of this ongoing cosmic lockout. No alarm sounds when a galaxy crosses the threshold. No announcement marks its departure from possible contact. The process occurs silently, invisibly, continuously. But the truly disturbing revelation lies not in what expansion has already done, but in what acceleration guarantees it will do. The universe is not merely expanding, it is expanding faster every moment. And this acceleration transforms eventual isolation into accelerating isolation, with profound implications for everything humanity might hope to achieve across cosmic time. In 1998, 2 independent teams of astronomers made a discovery that shocked the scientific community and would eventually earn them the Nobel Prize. They were studying Type Ia supernovae, stellar explosions with consistent brightness that serve as cosmic distance markers. These explosions occur when white dwarf stars accumulate enough matter from companion stars to trigger runaway thermonuclear fusion. The physics governing these detonations produces remarkably uniform peak luminosity, making them ideal standard candles for measuring cosmic distances. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, operated as friendly competitors, each racing to map cosmic expansion history. Both teams expected to measure how much gravity had slowed expansion since the Big Bang. By comparing how bright these supernovae appeared versus how bright they should be at their calculated distances, scientists could map the expansion history of the universe with unprecedented precision. Nearby supernovae established the baseline brightness. Distant supernovae revealed how expansion rates had changed over cosmic time. If gravity was slowing expansion as expected, distant supernovae would appear slightly brighter than their redshifts alone predicted. The universe would be smaller than a constant expansion rate implied, making distant objects appear closer and therefore brighter. The results made no sense. Distant supernovae appeared dimmer than expected. Not slightly dimmer, significantly dimmer. The discrepancy exceeded any reasonable measurement error. Something was wrong with either the observations or the theoretical predictions. Both teams triple-checked their data. They examined their instruments for calibration errors. They considered whether dust between galaxies might be absorbing light, making distant supernovae appear artificially dim. They wondered whether distant supernovae might differ systematically from nearby ones due to chemical evolution of the universe. Every alternative explanation fell short. Perlmutter's team announced preliminary results at a January 1998 conference, suggesting that expansion was accelerating rather than decelerating. The audience reacted with skepticism bordering on disbelief. Accelerating expansion contradicted everything. Cosmologists thought they knew about the universe. Gravity pulls matter together. The mutual attraction between all cosmic matter should slow expansion over time. Acceleration required something pushing space apart, some repulsive force overwhelming gravity on cosmic scales. Nothing in established physics predicted such a force. Weeks later, the High-Z team independently confirmed the same impossible result. Two competing groups using different telescopes, different analysis methods, and different team members had reached identical conclusions. The universe was not merely expanding, it was expanding faster every moment. The cosmic speed limit was not constant, it was accelerating. The scientific community responded with a mixture of excitement and profound unease. If the results were correct, they represented one of the most important discoveries in the history of cosmology. But extraordinary claims require extraordinary evidence. Both teams faced intense scrutiny as other researchers attempted to find flaws in their methods or alternative explanations for their data. The scrutiny only strengthened the case for acceleration. Independent analyses confirmed the supernova measurements. Alternative explanations involving dust absorption or supernova evolution failed to match the observed patterns. Within a few years, the scientific consensus shifted from skepticism to acceptance. The universe was accelerating, and cosmology would never be the same. The unavoidable conclusion emerged slowly, reluctantly, against the expectations of the astronomers themselves. Space was expanding faster than predicted. Not just expanding, accelerating. The universe was not merely growing larger, it was growing larger at an ever-increasing rate. Something was pushing space apart. Overwhelming gravity's attractive influence, driving galaxies away from each other faster with every passing moment. Scientists named this mysterious force dark energy. Dark energy comprises approximately 68% of the total energy content of the universe. This staggering percentage means that the dominant component of cosmic reality remains almost entirely mysterious. We know dark energy exists because we observe its effects. We can measure how it influences cosmic expansion with remarkable precision, but we have no idea what it actually is. The leading theoretical explanation identifies dark energy with vacuum energy, the quantum mechanical energy inherent in empty space itself. Quantum field theory predicts that even perfect vacuum seethes with virtual particles constantly popping into and out of existence. This quantum foam should carry energy, an energy curves space-time according to general relativity. Vacuum energy would naturally produce the kind of repulsive gravitational effect that dark energy exhibits. But calculations of vacuum energy from quantum field theory miss the observed value by roughly 120 orders of magnitude. This represents perhaps the worst prediction in the history of physics. The theoretical value exceeds the observed value by a factor of 10 followed by 120 zeros. If our understanding of quantum mechanics were correct in this domain, the vacuum energy should be so enormous that atoms could not form, stars could not ignite, and the universe would have torn itself apart moments after the Big Bang. Something fundamental remains missing from our understanding of how quantum mechanics and gravity interact. None of these explanations have gained universal acceptance. Dark energy remains one of the deepest mysteries in modern physics. Decades of research have constrained its properties without revealing its nature. We know how dark energy behaves without understanding what it is. This situation represents one of the most profound gaps in human knowledge about the cosmos we inhabit. But whatever dark energy actually is, we know exactly what it does. It accelerates cosmic expansion in a way that transforms humanity's cosmic future. Dark energy pervades all of space with a constant density that does not dilute as the universe expands. This property distinguishes it fundamentally from matter and radiation. When space stretches, matter spreads out. Double the volume and matter density drops by half. The same mass occupies larger space, reducing concentration proportionally. The same principle applies to radiation, which additionally loses energy as its wavelengths stretch with expanding space. Photons become less energetic as space grows, further reducing radiation's influence over cosmic evolution. But dark energy maintains the same strength everywhere, regardless of how much space expands. A cubic meter of space contains the same dark energy density today as it will contain in 1 billion years. Even though that cubic meter will have expanded enormously, this constancy seems counterintuitive. How can something maintain constant density while the volume containing it increases? The answer lies in the nature of dark energy as a property of space itself. Each new cubic meter of space comes with its own quota of dark energy. The density remains constant because the total amount increases in proportion to volume. This property creates a cumulative effect that strengthens over cosmic time. As space expands, new space is created everywhere. Each new cubic meter of space contains its own dark energy. The total amount of dark energy in the universe, therefore, increases as the universe grows. More dark energy means more acceleration. More acceleration means faster expansion. Faster expansion creates more space, which contains more dark energy, which drives more acceleration. This feedback loop explains why cosmic expansion accelerates rather than remaining constant. The engine driving universal growth becomes more powerful as that growth continues. Unlike matter and radiation, which dilute and weaken as the universe expands, dark energy compounds its influence without limit. The universe does not merely grow, it grows faster and faster, with no mechanism to slow or reverse the trend. The mathematics of accelerating expansion transforms the cosmic event horizon from a static boundary into a closing door. Consider what happens over billions of years. Dark energy continues, pushing space apart at an ever-increasing rate. The recession velocity at any given distance grows larger. A galaxy that today recedes at half the speed of light will eventually recede at the full speed of light, then faster still. The threshold where recession velocity equals light speed creeps closer to Earth. This threshold marks the Hubble sphere, the boundary where cosmic expansion exactly matches light speed. As expansion accelerates, this boundary shrinks relative to the galaxies it once contained. Galaxies that currently lie within the Hubble sphere will eventually find themselves beyond it. Their recession velocities will cross the critical threshold where expansion carries them away faster than light can travel toward us. But more importantly, the cosmic event horizon also shrinks. This horizon marks the absolute limit of possible causal contact, accounting for all future changes in expansion rate. As acceleration steepens, this horizon draws inexorably closer. Galaxies currently within our event horizon will cross beyond it. The volume of space that humanity could ever theoretically reach diminishes with every passing moment. This is not speculative physics. This is confirmed observation applied to known cosmological models. The lambda CDM model, which represents our best current understanding of cosmic evolution, incorporates dark energy as a cosmological constant with precisely measured properties. This model has survived every observational test thrown at it over the past 2 decades. Its predictions for cosmic acceleration match observations with remarkable accuracy. Different research teams using different methods have verified its conclusions repeatedly. The model predicts that the observable universe will shrink dramatically over coming billions of years. Not because space contracts, space continues expanding faster than ever, but the volume from which light can reach us diminishes as expansion accelerates beyond light speed at ever closer distances. The cosmic horizon closes in, even as the space beyond it expands without limit. Galaxies currently visible in our telescopes will fade from view one by one. Photons that departed these galaxies millions of years ago will arrive at Earth increasingly redshifted. Their energies depleted by the expansion they traveled through. Eventually, recession velocities will cross the threshold, where no new photons can ever reach us. These galaxies will not explode or disappear. No catastrophe will befall them. They will simply vanish from our cosmic neighborhood as expansion carries them beyond all possible contact. One moment, visible in our most powerful telescopes. The next moment, gone forever. Not destroyed, merely unreachable. The timeline of this cosmic disappearance unfolds across billions of years, but specific structures face specific fates that can be calculated with disturbing precision. The Coma Cluster, a massive concentration of over 1,000 galaxies approximately 320 million light-years distant, will remain visible for many billions of years, but expansion will eventually carry it beyond the event horizon. Astronomers of the far future will watch its galaxies redshift toward invisibility, their light stretching to undetectable wavelengths over timescales measured in billions of years. Eventually, no trace will remain detectable by any conceivable instrument. 1,000 galaxies, containing trillions of stars and countless worlds, simply vanishing from possible observation. The Perseus Cluster, home to thousands of galaxies at 240 million light-years distance, faces similar fate on similar timescales. The Shapley Supercluster, one of the most massive structures in the observable universe at 650 million light-years, will disappear sooner. Greater distance means earlier crossing of the event horizon. The most distant structures visible today have already crossed. We see their ancient light, while their current locations lie forever beyond reach. The Virgo cluster illustrates this coming isolation with particular immediacy. This massive structure contains more than 1,300 galaxies concentrated within a volume roughly 15 million light-years across. It lies approximately 54 million light-years from Earth, close enough to significantly influence our cosmic neighborhood. The Virgo cluster pulls the Milky Way toward it at speeds of several hundred kilometers per second. We are falling toward Virgo even as cosmic expansion carries more distant structures away. Currently, the Virgo cluster remains gravitationally significant to our local group. Filaments of dark matter and gas connect these structures through the cosmic web. Galaxy motions throughout this region reflect the gravitational interplay between Virgo's massive concentration and our smaller galactic neighborhood. The connection seems robust. Over cosmic time, even this relatively nearby structure faces potential separation from our local group. The critical question is whether gravitational attraction between Virgo and our local group can overcome cosmic expansion. Current measurements place this interaction near the boundary between binding and separation. The outcome depends sensitively on the precise masses involved and the exact behavior of dark energy overcoming billions of years. Small uncertainties in these parameters translate into radically different long-term futures. Most calculations suggest that the Virgo cluster will eventually drift beyond our cosmic event horizon. The expansion of space between our local group and Virgo will accelerate until it exceeds the gravitational attraction pulling us together. The connection will stretch thin, then break entirely. Virgo will recede beyond possible contact. carrying its 1,300 galaxies into permanent isolation from humanity. This brings us back to the fundamental constraint that dark energy acceleration makes permanent. Gravitational binding represents the only defense against cosmic isolation. Structures where mutual gravitational attraction exceeds cosmic expansion will remain together. Everything else separates, inevitably and permanently. The Laniakea supercluster, our larger cosmic neighborhood, demonstrates this principle at grander scales. Identified in 2014 through careful mapping of galaxy motions, Laniakea contains approximately 100,000 galaxies spread across 520 million light-years. This enormous structure includes the Virgo cluster, our local group, and thousands of other galaxy groups and clusters, all flowing toward a gravitational concentration called the Great Attractor. Despite this apparent coherence, Laniakea is not gravitationally bound. The structure exists because its components happen to be flowing in similar directions, drawn toward common gravitational wells. But expansion will eventually overcome these flows. Individual clusters and groups within Laniakea will separate as space between them stretches faster than gravity can pull them together. The supercluster that appears unified in current maps will fragment into isolated islands. Galaxy clusters will lose contact with their former neighbors. Groups will drift apart until each occupies its own shrinking patch of accessible space. The cosmic web connecting these structures will stretch thin, fade, and finally disappear entirely. Where vast filaments once channeled matter across hundreds of millions of light-years, only empty voids will remain. Scientists model this future isolation using sophisticated cosmological simulations. These computer programs track the evolution of millions of simulated galaxies over billions of years, incorporating dark energy's accelerating influence. The simulations begin with initial conditions matching observed cosmic structure, then project forward to reveal how expansion will reshape the universe. The results consistently show the same outcome. Increasingly isolated islands of galaxies surrounded by expanding voids of empty space. Structures that appear connected today gradually separate. Filaments linking galaxy clusters stretch until they snap. Voids expand to consume the space where cosmic web once existed. The universe transitions from a connected network to scattered archipelagos of matter drifting through infinite emptiness. The rate of this isolation depends on the precise properties of dark energy. Current observations constrain dark energy behavior to a narrow range of possibilities, but significant uncertainty remains. The most likely scenario involves a cosmological constant, a fixed energy density that remains unchanged as the universe evolves. Einstein originally introduced this concept to produce a static universe, then abandoned it when expansion was discovered. Ironically, it has returned as the best explanation for accelerating expansion. A cosmological constant produces steady acceleration that compounds over cosmic time. Expansion rates increase at a predictable pace, roughly doubling every 10 billion years. This gentle but relentless acceleration gradually isolates cosmic structures over timescales measured in hundreds of billions of years. The universe does not end in fire or ice. It ends in separation, as expansion carries all structures beyond mutual contact. Some theoretical models propose dark energy that strengthens over time, a scenario called phantom energy. Under these models, dark energy density increases as the universe expands rather than remaining constant. This produces acceleration that grows faster than the already accelerating standard scenario. If phantom energy proves real, cosmic isolation will occur more rapidly than current models predict. Phantom energy creates a disturbing endpoint called the Big Rip. As acceleration intensifies without limit, it eventually overcomes every force in nature. First, galaxy clusters are torn apart as expansion overwhelms gravitational binding between member galaxies. Then, individual galaxies dissolve as expansion overcomes the gravity holding them together. Stars are stripped from galactic centers and cast into expanding voids, But phantom energy does not stop there. Eventually, acceleration overcomes electromagnetic forces, binding molecules together. Materials disintegrate into component atoms as the forces holding them together become insufficient against expanding space. Then nuclear forces binding atoms together succumb. Electrons are stripped from nuclei. Finally, the strong force binding atomic nuclei together fails. Protons and neutrons dissolve into quarks. In the final moments before the Big Rip, space expands so rapidly that it tears apart the fundamental constituents of matter itself. Current observations slightly disfavor phantom energy scenarios. The data suggests that cosmic acceleration will continue, but not reach such catastrophic extremes. Dark energy appears consistent with a cosmological constant rather than increasing phantom energy. The universe will likely experience increasing isolation rather than violent destruction. Galaxies will drift apart forever rather than being torn to pieces. But even the gentler scenario of steady cosmic acceleration produces outcomes that shatter dreams of intergalactic civilization. Consider the timeline of cosmic isolation in concrete terms. Within approximately 2 billion years, galaxies currently receding at moderate velocities will cross the cosmic event horizon. These are galaxies astronomers can observe and photograph today. Their light has reached us across billions of light-years of space, carrying information about stellar populations and galactic structures. But the galaxies themselves, as they exist right now, have already passed beyond possible contact. We see their ancient past, while their present and future lie forever beyond reach. Within approximately 50 billion years, the great galaxy clusters that currently dominate cosmic structure will have receded beyond the event horizon. The Coma cluster, the Perseus cluster, the Shapley supercluster. All will have vanished from possible observation. The cosmic web connecting these structures will have dissolved. The universe will appear increasingly empty as more and more structures cross beyond detectability. Within approximately 100 billion years, essentially all galaxies outside our local group will vanish from the observable universe. The night sky will contain only our local galactic neighbours. Andromeda will dominate, along with a few dozen smaller companion galaxies. The rest of the cosmos will have vanished into permanent inaccessibility. The cosmic microwave background radiation will stretch to undetectable wavelengths. This ancient light, which currently fills all of space with faint microwave glow, will redshift into radio waves, then into wavelengths too long for any conceivable instrument to detect. The echo of the Big Bang will fall silent. Within approximately 1 trillion years, even the faintest distant light will have faded beyond detection. The observable universe will shrink to encompass only gravitationally bound structures. Future astronomers will see a cosmos that appears almost empty. Perhaps 80 galaxies in their local group, perhaps a few hundred more if Virgo remains bound. Nothing else. These future observers will face a profound epistemological crisis that strikes at the heart of scientific inquiry. Their universe will appear static and eternal. No expanding cosmos, no Big Bang history, no evidence of the vast structure that once filled observable space. Consider what evidence future scientists will lack: the cosmic microwave background, that ancient echo of the Big Bang, will have stretched beyond detection. This radiation currently provides our most direct evidence of cosmic origins. Its precise temperature and subtle fluctuations encode information about conditions when the universe was only 380,000 years old. Future astronomers will have no access to this crucial data. The redshift of distant galaxies, which revealed expansion to Hubble, will be unobservable because no distant galaxies will remain visible. Hubble's discovery depended on observing many galaxies at various distances and noting the systematic relationship between distance and redshift. Future observers will see only local galaxies, which show complex motions dominated by gravity rather than cosmic expansion. They will have no way to discover that the universe is expanding. The supernova observations that revealed dark energy acceleration will be impossible because all supernovae beyond the local group will occur in unreachable space. The 1998 discovery required observing stellar explosions in galaxies billions of light-years distant. Future astronomers will see supernovae only in their local galactic neighborhood, providing no information about cosmic expansion history. Future scientists might develop brilliant theories about cosmic origins. They might hypothesize that their island of galaxies emerged from a hot, dense state. They might speculate about expansion and acceleration, but they will have no way to test these theories. The evidence will have literally been carried away by the very expansion it would have revealed. This epistemic isolation represents a profound asymmetry in cosmic history. Humanity exists during a brief window when the universe still reveals its structure and history. We can see billions of galaxies. We can detect the cosmic microwave background. We can measure expansion rates across cosmic time. We can trace cosmic history back to the first moments after the Big Bang. This knowledge is not permanent. It is a temporary gift of cosmic timing. Future civilizations will lack this privilege. They will inherit a cosmos stripped of its evidence, a mystery without clues. Whatever cosmological theories they develop will be untestable against observations that no longer exist. They might develop sophisticated physics, describing hypothetical cosmic expansion. They might postulate a Big Bang origin, but they will never be able to verify these ideas through observation. The universe will have erased its own history, not through destruction, but through expansion. The evidence will not be lost. It will simply become unreachable, carried beyond the event horizon by the very phenomenon it documents. All of this brings us back to the inescapable reality that expansion acceleration makes permanent. No matter how advanced technology becomes, future civilizations cannot recover what expansion has taken. The galaxies that vanish beyond the event horizon are not hiding somewhere waiting to be found. They are entering a state of permanent causal separation from which nothing can return. Current observations allow us to quantify this cosmic shrinkage with disturbing precision. The local group contains approximately 80 galaxies within a volume spanning roughly 10 million light-years. The Milky Way and Andromeda dominate this collection, with dozens of smaller dwarf galaxies orbiting these spiral giants. Gravitational binding ensures these galaxies will remain accessible to each other, regardless of how much the broader universe expands. This represents our gravitational island, the region where mutual attraction overcomes cosmic expansion. Everything within this island remains permanently accessible. In principle, a sufficiently advanced civilization could eventually visit any location within the local group, given enough time and appropriate technology. Everything else is slipping away. The cosmic event horizon currently sits at approximately 16 billion light-years. Galaxies beyond this distance are already unreachable. But the horizon is not static. As dark energy acceleration continues, this boundary will creep steadily inward. Galaxies currently within our event horizon will cross beyond it. The volume of accessible space will shrink. Scientists project that the event horizon will eventually stabilize near the edge of our local group. The precise boundary depends on dark energy's exact properties and the gravitational dynamics of local structures, but the outcome is clear. Everything beyond our immediate gravitational neighborhood will eventually become permanently inaccessible. The process is invisible and silent. No explosion marks the moment when a galaxy crosses the threshold. No signal announces its departure from possible contact. Astronomers cannot observe the event horizon directly. They can only calculate its location based on measured expansion rates and project how it will evolve. Galaxies crossing the horizon will not suddenly vanish from telescopes. Light that departed these galaxies millions of years ago continues traveling toward us, arriving increasingly redshifted as expansion stretches its wavelengths. The galaxies will appear to slow down as they approach the horizon. their images frozen in time at the moment of crossing. Eventually, their light will stretch beyond detection, fading into invisibility rather than disappearing suddenly. But the fading is permanent. Once a galaxy crosses the event horizon, no new light from that galaxy will ever reach Earth. The final photons to depart before the crossing will arrive eventually, completing a journey that began before the separation became permanent. Then silence. Forever. Every second that passes, dark energy adds to the cumulative effect of cosmic acceleration. The universe is actively shrinking from humanity's perspective. The boundary of what we can ever reach, ever visit, ever influence, is drawing closer. This is not a wall we might someday breach. It is the fundamental structure of how space and time evolve. Dark energy is not a force we might overcome. It is the property of space itself, woven into the fabric of the cosmos at levels we are only beginning to understand. Some might hope that future physics will reveal ways to counteract dark energy or exploit its properties for interstellar travel. Scientists remain appropriately humble about the limits of current understanding. New discoveries might reshape our picture of cosmic acceleration, but the observations are not going away. Whatever dark energy actually is, its effects are measured and confirmed through multiple independent methods. Expansion is accelerating. The event horizon is shrinking. These facts will not change regardless of what theoretical explanations eventually prove correct. The implications extend far beyond academic cosmology. They define the ultimate boundaries of human possibility. They establish that most of the universe we can observe is already lost to us, and they guarantee that what remains accessible will shrink continuously until almost nothing remains within reach. Beyond the event horizon lies more than 97% of the observable universe. Trillions of galaxies containing countless stars and planets, structures spanning billions of light years that humanity will never explore. Potential civilizations separated from us by distances that expansion makes permanently uncrossable. We exist during a brief window of cosmic history when the universe still reveals itself to observation. Future intelligence may persist for trillions of years in a cosmos that appears almost empty. They will never know what we can still see. They will never reach what has already passed beyond our reach. The shrinking horizon marks the true boundary of cosmic existence, and it draws closer with every passing moment. The James Webb Space Telescope has revealed galaxies that formed when the universe was only a few 100 million years old. These ancient structures, sitting more than 13 billion light-years away, appear in stunning detail through Webb's infrared instruments. Astronomers can discern individual star-forming regions within these primordial galaxies. They can measure chemical compositions that reveal the first generations of stellar nucleosynthesis. They can trace the assembly of cosmic structure during an era when the universe was less than 5% of its current age. Their light has travelled across almost the entire history of cosmic time to reach our instruments. Photons that departed these galaxies began their journey before Earth existed, before our Sun ignited, before the Milky Way assumed its current spiral form. These ancient messengers carry information about conditions that prevailed when the cosmos was young, hot, and dense with star formation. Each photon represents a tiny fragment of cosmic history, preserved across billions of years of travel. Scientists study their properties to understand how the first stars ignited and how galaxies assembled from primordial gas. Webb's observations have already challenged theoretical models of early galaxy formation. Galaxies appear more massive and more structured at early cosmic epochs than simulations predicted. The universe apparently built complex structures faster than astronomers expected. These discoveries reshape our understanding of cosmic evolution. These galaxies are already gone, not destroyed, not collapsed, simply unreachable. Their light departed when they were relatively close to our cosmic neighborhood. 13 billion years ago, cosmic expansion had not yet carried these structures beyond the event horizon. The photons we detect tonight escaped before the door closed. But during the 13 billion years that light traveled toward us, cosmological expansion carried those galaxies far beyond any possible contact. Calculate the distances involved and the scale of separation becomes clear. When light left these ancient galaxies, they sat perhaps 1 billion light-years away, close enough that photons traveling at the cosmic speed limit could eventually bridge the gap. The early universe was smaller, denser, more compact. Distances between structures were measured in millions or low billions of light-years, rather than the tens of billions that separate us today. But space stretched continuously during the journey. Every moment of those 13 billion years, expansion added new distance between the travelling photons and their destination. The galaxies receded as their light approached. The photons made progress through local space, while the space itself grew faster than they could traverse it. By the time Webb captures their ancient images, those same galaxies have been carried more than 40 billion light-years distant, far beyond the cosmic event horizon. Forever unreachable, the light we capture tonight represents a concluding dispatch from structures that passed beyond contact billions of years ago. We observe their ancient images while knowing that their current locations lie in regions of space that humanity can never visit. The galaxy's Webb photographs are ghosts, echoes of structures that have long since passed beyond possible contact. We see where they were, not where they are, and where they are lies beyond any conceivable journey. This distinction between what we can see and what we can reach represents one of the most counterintuitive aspects of modern cosmology. Human intuition assumes that observation implies accessibility. If we can see something, surely we can eventually go there. Light travelled from that location to reach our eyes. The path exists. The connection has been made. We should be able to reverse the journey, travelling from our eyes back to that location. Cosmic expansion shatters this intuition completely. The observable universe extends 46.5 billion light-years in every direction. This enormous sphere encompasses everything from which light has had time to reach Earth since the Big Bang. It contains approximately 2 trillion galaxies, each harbouring billions of stars. The total number of stars within our observable volume exceeds the number of grains of sand on every beach on Earth. The scale defies comprehension. More galaxies than any human could count in a lifetime. More stars than any census could enumerate. But the reachable universe, the region to which we could ever send a signal or spacecraft, measures only 16 billion light-years at maximum. This represents the cosmic event horizon, the boundary beyond which no influence from Earth can ever propagate regardless of how much time passes or what technologies develop. The math reveals the staggering implications. Volume scales with the cube of radius. The observable universe, with its radius of 46.5 billion light-years, contains a volume of approximately 4 sextillion cubic light-years. The theoretically reachable universe, bounded by the event horizon at 16 billion light-years, contains roughly 17 trillion cubic light-years. Compare these figures. The reachable volume amounts to approximately 3% of the observable volume. 97% of everything we can observe has already passed beyond any possible contact. The overwhelming majority of the cosmos visible in our telescopes lies forever beyond human reach. Consider what this percentage represents in concrete terms. Of approximately 2 trillion galaxies in the observable universe, fewer than 60 billion remain even theoretically accessible. The rest have crossed beyond the event horizon. Approximately 1,940 billion galaxies exist in regions of space permanently cut off from Earth. Each of those galaxies contains billions of stars. Each of those stars might host planets. The numbers of potentially habitable worlds beyond our reach exceed any meaningful comprehension. But even the calculation of theoretically reachable galaxies overstates our practical cosmic domain. Reaching the edge of the theoretically reachable universe requires travel at light speed for 16 billion years. The laws of physics prohibit accelerating any massive object to that velocity. The energy required approaches infinity as speed approaches light speed. Even photons, which travel at light speed by nature, require 16 billion years to reach the event horizon. Practical spacecraft achieve only tiny fractions of light velocity. The fastest human-made objects, like the Parker Solar Probe during its closest solar approaches, reach speeds of roughly 190 kilometers per second. This represents approximately 1/1600th of 1% of light speed. At this velocity, reaching the event horizon would require more than 2 quadrillion years. The universe would have long since faded into cold darkness before such a journey could complete. Even the most optimistic propulsion concepts achieve only modest fractions of light velocity. Theoretical designs for nuclear pulse propulsion, antimatter rockets, or laser-pushed light sails might achieve 10% of light speed under extraordinarily favorable assumptions. These technologies remain speculative, requiring engineering breakthroughs that may or may not prove possible. They represent the extreme upper limit of what physics might conceivably permit. Consider a spacecraft traveling at 10% of light speed, which represents an extraordinarily optimistic assumption given current technology. Such a vessel would require 160 billion years to reach the edge of the theoretical maximum, but the universe is only 13.8 billion years old. The spacecraft would be traveling for more than 10 times the current age of the cosmos. During that journey, cosmic expansion would continue accelerating. Dark energy would drive space apart at ever-increasing rates. The destination would recede faster than the spacecraft could approach. Each billion years of travel would see the target slip further away rather than drawing closer. The vessel would never arrive. It would chase a receding horizon forever, falling further behind with each passing billion years. Even at 10% of light speed, even with unlimited fuel and perfect engineering, even with crews willing to travel for hundreds of billions of years, the journey would fail, not because of insufficient technology, because expansion creates distance faster than any travel can cross it. This brings us back to the fundamental reality that expansion creates and that no technology can circumvent. The vast majority of the observable universe was never reachable, and never will be. Light from these regions reaches us only because their photons departed before expansion carried them away. We receive final communications from galaxies that have already crossed into permanent isolation. The cosmic web structure makes this isolation even more stark and reveals the architecture of our cosmic prison. Galaxies do not distribute randomly through space. They cluster along vast filaments of dark matter that stretch across hundreds of millions of light years. These filaments form a three-dimensional network resembling soap foam or neural tissue. Dense nodes mark the intersections where multiple filaments meet. Galaxy clusters concentrate at these nodes, containing thousands of galaxies bound together by mutual gravitation. Between filaments lie enormous voids containing almost nothing. These cosmic deserts span hundreds of millions of light years, their interiors nearly empty of galaxies. A few scattered dwarf galaxies drift through void regions, but the overwhelming majority of cosmic matter concentrates along filaments and within clusters. The contrast between filaments and voids creates the distinctive pattern astronomers call the cosmic web. The cosmic web represents the largest coherent structures in the universe. Individual filaments span hundreds of millions of light years. The network connects galaxy clusters across billions of light years of space. Mapping this structure has occupied astronomers for decades, requiring surveys of millions of galaxies to reveal the underlying pattern. But this magnificent architecture is temporary. Expansion is slowly dissolving the cosmic web. Consider what happens to a single filament as cosmic time progresses. Initially, the filament connects two galaxy clusters through a stream of dark matter and gas. Galaxies populate this stream, orbiting slowly as they drift toward one cluster or the other. The filament appears stable, a cosmic highway linking distant structures. Matter flows along its length. Galaxies cluster along its spine. The connection seems permanent, but expansion stretches the filament continuously. Space between the clusters grows. The filament thins as its material spreads across increasing volume. Dark matter density drops. Gas becomes more diffuse. Galaxies within the filament drift apart as the space containing them expands. Eventually, the filament ceases to exist as a coherent structure. The connection between the clusters it once linked breaks permanently. This process occurs throughout the cosmic web. Every filament faces the same fate. Every connection between distant structures will eventually stretch beyond coherence. The beautiful architecture, visible in current cosmic surveys, represents a temporary phase in universal evolution. Not a permanent arrangement, the largest structures dissolve first. Filaments spanning hundreds of millions of light-years stretch thinner than shorter connections. Superclusters fragment before smaller structures. The cosmic web unravels from the largest scales downward, like a tapestry whose longest threads fray first. This dissolution means that isolation does not happen uniformly. Entire superclusters of galaxies cross the event horizon together, like islands sinking beneath rising waters. The filaments connecting them stretch and thin until they snap, leaving isolated clusters drifting in expanding voids. The cosmic web does not merely fade, it fragments into increasingly isolated pieces. Laniakea, the supercluster discussed earlier, illustrates this fragmentation at the grandest scales. Despite 100,000 galaxies flowing toward the Great Attractor at its heart, this apparent coherence is temporary. The Great Attractor lies approximately 250 million light-years from Earth, hidden behind the Milky Way's obscuring disk until X-ray and infrared surveys revealed its true nature as a concentration of massive galaxy clusters. Galaxies throughout Laniakea flow inward at several hundred kilometers per second, pulled by the Great Attractor's immense gravitational influence. But as established, Laniakea is not gravitationally bound. These inward flows will eventually reverse as expansion accelerates beyond gravitational attraction. The supercluster will fragment over tens of billions of years, its component groups drifting apart until they cross beyond each other's event horizons. Where vast structure once connected hundreds of thousands of galaxies, only isolated remnants will remain. This brings us back to the only regions that will remain accessible across cosmic time. Gravitationally bound structures where mutual attraction exceeds expansion at every point within them. The local group represents our gravitational island. Approximately 80 galaxies are bound together by their combined gravitational influence. This collection spans roughly 10 million light-years, a tiny volume compared to cosmic scales, but the entirety of what humanity might ever actually reach. The Milky Way and Andromeda dominate this group, containing more than 90% of its total mass. These two spiral giants orbit their common center of mass on a collision course that will culminate in approximately 4.5 billion years. Their merger will create a massive elliptical galaxy that astronomers have nicknamed Milky-Way-Andromeda, combining the stellar populations of both parents into a single gravitationally bound structure. Smaller dwarf galaxies orbit these giants in complex patterns. The large and small Magellanic Clouds accompany the Milky Way, visible from the southern hemisphere as detached patches of galactic glow. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's tidal forces, its stars streaming into our galaxy. Dozens of ultra-faint dwarf galaxies lurk at the edges of detection, discovered only through careful surveys of stellar populations. Within the local group, cosmic expansion is overcome by gravitational attraction. The mutual pull between member galaxies exceeds the expansion rate at every point within the group's volume. These galaxies will remain accessible to each other, regardless of how much the broader universe expands. The local group represents a permanent fixture in an otherwise dissolving cosmos. Spacecraft launched from Earth could theoretically reach any location within the local group given sufficient time and propulsion. The distances remain enormous by human standards. Andromeda lies 2.5 million light-years distant. Even at 10% of light speed, the journey would require 25 million years. But the journey is possible in principle. Expansion does not prevent it. The destination will still be there when the spacecraft arrives. But the local group measures only 10 million light-years across. Compare this to the observable universe at 93 billion light-years. Our gravitational island represents roughly 1/1000th of 1% of the cosmic volume we can observe. Everything else lies beyond reach, either now or eventually. Beyond the local group, the next significant structure is the Virgo cluster. Approximately 54 million light-years distant, this massive cluster contains over 1,300 galaxies. As discussed earlier, Virgo sits at the uncertain boundary between gravitational binding and expansion-driven separation. Its fate remains one of the great unknowns of our cosmic future. If Virgo remains gravitationally connected to our local group, our cosmic island expands to include approximately 2,000 galaxies. If expansion eventually wins, the cluster will drift beyond our event horizon, carrying its 1,300 galaxies into permanent isolation. Either way, the numbers remain humbling. 2,000 galaxies at most from an observable universe containing 2 trillion, less than 1/1000th of 1% of cosmic structure. The rest lies beyond reach regardless of which scenario proves correct. All of this brings us back to the fundamental constraint that cosmological expansion enforces. The boundaries of human possibility are not technological, they are cosmological. The universe itself determines what can ever be reached, and it has already locked away almost everything we can see. Galaxies visible in the Hubble ultra-deep field illustrate this cosmic lockout with particular emotional force. This famous image, created by pointing the Hubble Space Telescope at an apparently empty patch of sky for hundreds of hours, revealed approximately 10,000 galaxies in a field smaller than a grain of sand held at arm's length. Extrapolating across the entire sky suggested that the observable universe contains hundreds of billions of galaxies, later revised upward to approximately 2 trillion when accounting for faint galaxies below Hubble's detection threshold. Consider one particular galaxy visible in the ultra-deep field. Pick any smudge of light from among the thousands. That galaxy contains perhaps 100 billion stars. Around those stars orbit planets numbering in the hundreds of billions. Some fraction of those planets sit within habitable zones where liquid water could exist. On some fraction of those habitable worlds, conditions might have allowed life to emerge. On some fraction of those living worlds, intelligence might have evolved. We will never know. That galaxy crossed beyond the cosmic event horizon billions of years ago. Its current location lies tens of billions of light-years distant, in regions of space where expansion exceeds light speed. No signal we send can ever reach it. No spacecraft we launch can ever arrive there. No future technology can bridge the gap because the gap grows faster than any technology could close it. The photons reaching our detectors tonight are the concluding chapter of a story we can never finish reading. Ancient light, completing a journey that began before Earth existed. By the time we photograph this galaxy, every star it contained when that light departed has long since evolved. Some have died as supernovae. Others have faded into white dwarfs. New stars have formed from their remnants. The galaxy itself has likely merged with neighbours, been disrupted by gravitational interactions, evolved beyond recognition from the ancient image we observe. We see a snapshot frozen in cosmic time, a postcard from a place that no longer exists as photographed, a message from structures that might have evolved complex chemistry, life, even intelligence while their light travelled toward us. We will never know their story, because their story lies beyond the event horizon, forever inaccessible. This creates a profound asymmetry in cosmic observation. We can look backward in time, across almost the entire history of the universe. Light from the cosmic microwave background shows conditions 380,000 years after the Big Bang, when the universe first became transparent to radiation. Light from distant quasars reveals conditions when the universe was less than 1 billion years old. Light from ancient galaxies displays cosmic evolution across 13 billion years. But we can never look forward. We can never observe the current state of galaxies beyond the event horizon. We can never know what those structures have become in the billions of years since their light departed. Have they merged with neighbors? Have their stars burned out? Have civilizations risen and fallen within them? The universe shows us an extensive past while hiding an overwhelming present. Causal separation is physically permanent. This principle, established by the very nature of space-time, defines the ultimate boundary of human existence. No amount of technological progress can change what causality means. No future discovery can bridge gaps where no physical influence can propagate. The event horizon marks where this separation becomes absolute. Beyond it, no signal sent from Earth can ever arrive. No spacecraft can ever reach those destinations. No information, no matter, no influence of any kind can cross from our cosmic neighborhood into those forever inaccessible regions. The isolation is complete and woven into the fabric of reality itself. Beyond this horizon, galaxies continue their cosmic evolution in complete isolation from Earth. Stars form from collapsing gas clouds, burn through their nuclear fuel, and expire as white dwarfs, neutron stars, or black holes. Planets orbit in configurations we will never map. Atmospheres contain compositions we will never analyze. Geology follows processes we will never study. Perhaps civilizations rise in those distant galaxies. Perhaps intelligent beings develop technology and science. Perhaps they ask questions about the cosmos, study physics and astronomy, wonder whether they are alone in the universe. They will never know about Earth. We will never know about them. The causal separation is absolute. We are witnesses to our own exclusion, observers of a cosmos that has already departed. We share a universe with structures we can never contact. We observe a cosmos we can never explore. The great lockout is not coming. It has already happened. 97% of the observable universe lies beyond the cosmic event horizon. The light arriving from these regions carries the last whispers of a cosmos already lost to us. What remains accessible, however, deserves deeper examination. Within our gravitational island lies everything humanity might ever actually reach across cosmic time. The 80 galaxies of the local group, and possibly the additional structure of the Virgo cluster, represent the entirety of human cosmic possibility. Understanding this limited domain reveals both the boundaries and the possibilities that define our ultimate future among the stars. The Andromeda galaxy hangs in the autumn sky as a faint smudge of light visible to the naked eye. From a dark location far from city lights, this ghostly oval appears roughly 6 times wider than the full moon, though only its bright central core registers to unaided human vision. Most people have never noticed it. Light pollution washes it from suburban skies. Urban observers cannot see it at all, but from truly dark sites, Andromeda reveals itself as a pale, elongated glow, unremarkable among the brighter stars surrounding it. Ancient astronomers catalogued this smudge without understanding its nature. Persian astronomer Abd al-Rahman al-Sufi described it around 964 CE as a little cloud in his Book of Fixed Stars. European astronomers rediscovered it centuries later. For 1,000 years, humanity gazed at Andromeda without comprehending what it represented. A smudge of light. A nebula, perhaps. A cloud of gas within our own stellar system. Modern observations reveal Andromeda as a spiral structure containing more than 1 trillion stars spread across 220,000 light-years. This makes it larger than our own Milky Way, which spans roughly 100,000 light-years and contains approximately 400 billion stars. Andromeda possesses its own system of satellite galaxies, its own population of globular clusters, its own spiral arms winding outward from a dense central bulge. At its heart lurks a supermassive black hole with a mass of approximately 100 million suns, roughly 25 times more massive than Sagittarius A star, the 4 million solar mass black hole at the Milky Way's center. Andromeda represents the most significant cosmic neighbor humanity will ever have. The distance separating our galaxies measures 2.5 million light-years. Light departing Andromeda tonight will reach Earth in 2.5 million years. Our earliest human ancestors were just beginning to craft stone tools when the light now reaching our telescopes departed Andromeda. Signals transmitted from Earth tonight will arrive at Andromeda on the same timescale. Future species descended from humanity, if any survive, might receive responses to messages we send today. This represents genuine causal contact. Events in our galaxy can influence events in Andromeda. The gravitational dance already binding these spirals together demonstrates this connection directly. We are not isolated from Andromeda. We are falling toward it, but Andromeda is not merely our neighbor, it is our destiny. Precise measurements of Andromeda's motion reveal that it approaches the Milky Way at approximately 110 kilometers per second. This blue shift, opposite to the red shift displayed by most galaxies, indicates that gravitational attraction between our spirals overcomes cosmic expansion at this distance. While the universe carries distant galaxies away from us, Andromeda draws closer with every passing moment. The gap between our galaxies shrinks by approximately 110 kilometers every second. This approach has continued for billions of years and will continue for billions more. Computer simulations model the approaching merger with remarkable precision. Astronomers have constructed detailed numerical models incorporating the masses, velocities, and dark matter distributions of both galaxies. These simulations track millions of simulated star particles, calculating gravitational interactions across billions of years of cosmic evolution. The models reveal the intricate gravitational choreography that will transform both spirals into something entirely new. The two galaxies will begin interacting gravitationally within approximately 3 billion years. At this stage, they will still appear as separate structures, but tidal forces will begin distorting their shapes. Andromeda's gravitational pull will stretch the Milky Way's spiral arms. Long streamers of stars will extend from both galaxies as gravitational tides pull material from their outer regions. The elegant spiral patterns that currently characterize both galaxies will begin to warp and distort. First close passage will occur approximately 4 billion years from now. The galactic cores will sweep past each other at distances of perhaps 50,000 light-years, close enough for dramatic gravitational interaction, but not direct collision. The encounter will fling stars into chaotic new orbits. Some will be ejected entirely, cast into intergalactic space as orphaned suns wandering alone through the void. Individual stars will rarely collide directly during this process. The spaces between stars are so vast that even during galactic merger, stellar collisions remain extraordinarily unlikely. If you shrank the Sun to the size of a grain of sand, the nearest star would sit several miles away. Two galaxies passing through each other experience remarkably few direct stellar encounters, despite containing hundreds of billions of stars each. Stars pass between other stars like birds from two flocks flying through each other. The flocks merge while individual birds almost never touch, but gravitational chaos will reshape both galaxies beyond recognition. After first passage, the two spirals will separate briefly, their mutual gravity slowing their recession, then fall back together for a second encounter. Each passage strips more material from each galaxy, mixing their stellar populations, destroying the ordered spiral structure that currently characterizes both. Computer simulations show the galaxies bouncing apart and falling back together multiple times over approximately 2 billion years, like two water droplets colliding and eventually merging. The merger process will span approximately 6 billion years, from first interaction to final coalescence. During this extended cosmic dance, both galaxies will be transformed. Spiral arms will stretch, warp, and ultimately dissolve. The flat disk structures will puff up into spheroidal shapes as gravitational interactions scatter stars into random three-dimensional orbits. Streams and shells of stars will arc through space, tracing the gravitational history of the collision. Bursts of star formation will ignite across both galaxies during the merger. When galaxies collide, their gas clouds compress as gravitational tides squeeze interstellar material. This compression triggers the collapse of gas clouds that might otherwise have remained stable for billions of years. The merger will create new stellar nurseries where thousands of stars ignite simultaneously. For a period lasting perhaps 100 million years, the combined system will blaze with newborn stars, temporarily outshining its normal luminosity by significant factors. The supermassive black holes at each galactic center will spiral toward each other through a process called dynamical friction. As each black hole moves through the combined stellar population, gravitational interactions with passing stars gradually drain its orbital energy. The black holes will circle each other in an ever-tightening orbit, eventually approaching within light years of each other. The final merger of these black holes will release gravitational waves detectable across the universe. When two supermassive black holes finally coalesce, they convert a significant fraction of their combined mass into gravitational radiation. This energy output exceeds the light output of all stars in both galaxies combined. The gravitational wave signal will ripple outward at light speed, carrying news of the merger to any civilization with instruments capable of detecting it. The final product, already named Milky-Way by astronomers contemplating our distant future, will be a massive elliptical galaxy containing the combined stellar populations of both parents. The elegant spiral structure of both the Milky Way and Andromeda will have vanished entirely. In its place will sit a giant spheroid of stars orbiting the central supermassive black hole in random three-dimensional paths. Instead, stars would populate the sky in all directions with roughly equal density. No galactic plane would define a preferred orientation. No spiral arms would create the patchy brightness variations visible in our current night sky. The central bulge of the merged galaxy would blaze as a brilliant region of concentrated starlight, far brighter than any feature in our present sky. Looking toward the galactic center, observers would see a wall of stars too numerous to count, their combined light creating a permanent glow even on the darkest nights. The stellar density in Milky-Way's central regions would exceed current conditions in the Milky Way's core. Stars would pack more closely together, reducing typical separations. Planets in these dense regions would have skies permanently blazing with stellar light, their nights illuminated by thousands of nearby suns. The concept of true darkness would be foreign to any civilization arising in Milky-Way's heart. Approximately 1 trillion stars will populate this merged structure. The combined stellar mass will rival the largest galaxies anywhere in the observable universe. Milky-Way will become a dominant structure in the local cosmos, its gravitational influence extending across millions of light years. Nothing else nearby will compare in size or mass. Earth might survive this cosmic collision. Our solar system currently orbits the Milky Way at a distance of approximately 26,000 light-years from the galactic center. This places us well within the disk, but far from the central regions where gravitational interactions will be most violent. Simulations suggest that stars in our neighborhood have roughly even odds of being flung into larger or smaller orbits around the combined galactic center. Some simulations show our solar system ejected into intergalactic space. Others show it remaining bound to the merged galaxy in an extended orbit. The Sun will exhaust its hydrogen fuel and expand into a red giant before the merger completes, ending life on Earth through our star's natural evolution approximately 5 billion years from now. The merger's first dramatic phases will occur while Earth remains habitable. offering any descendants who survive that long, a spectacular view of galactic collision painted across the night sky. But the final coalescence will occur after the Sun has already consumed the inner planets during its red giant phase. This brings us back to the fundamental reality that defines humanity's cosmic future. The Andromeda merger illustrates what remains accessible across cosmic time. Despite the violence of galactic collision, despite the chaos of gravitational interaction, despite the transformation of familiar structures into something unrecognizable, Andromeda remains within reach. The merger itself proves the causal connection. Gravity can only act between structures that maintain causal contact. Beyond Andromeda, the Triangulum galaxy sits 3 million light-years distant. This smaller spiral contains approximately 40 billion stars, making it the third largest member of our local group. Triangulum orbits Andromeda in a complex gravitational dance that simulations suggest will end with its absorption during or shortly after the Milky Way-Andromeda merger. Where the two great spirals create Milkomeda, Triangulum will likely contribute additional stellar material to the final product. Approximately 80 galaxies populate the local group in total. Most are dwarf galaxies, small collections of a few billion or even a few million stars orbiting the dominant spirals. The large and small Magellanic Clouds accompany the Milky Way, visible from the southern hemisphere as detached portions of galactic glow. These irregular galaxies contain active star formation regions and serve as cosmic laboratories for studying stellar evolution at close range. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's tidal forces. Its stars stream into our galaxy in long, arcing trails that wrap around the Milky Way's disk. This ongoing merger demonstrates that galactic cannibalism occurs routinely on cosmic timescales. Our galaxy has consumed smaller neighbors before and will consume more in the future. Dozens of ultra-faint dwarf galaxies lurk at the edges of detection, discovered only through careful surveys that identify slight overdensities in stellar populations against the foreground of Milky Way stars. These ghostly structures contain only thousands or tens of thousands of stars each, barely qualifying as galaxies by some definitions, yet they remain gravitationally bound to the local group, destined to orbit the merged Milkomeda for billions of years to come. This entire collection spans roughly 10 million light-years. Everything within this volume remains gravitationally bound. Expansion cannot tear it apart. Dark energy cannot overcome the gravitational attraction holding these structures together. The local group represents a permanent cosmic structure, an island of accessibility in an increasingly isolated universe. But beyond this island, everything is leaving. And it is leaving faster every moment. The Virgo cluster might remain marginally accessible, sitting at the uncertain boundary between gravitational binding and expansion-driven separation. Current measurements cannot determine with certainty whether Virgo will remain connected to our local group or eventually drift beyond the event horizon. The answer depends on precise values of masses and distances that remain imperfectly known. But even if Virgo remains reachable, it merely extends our cosmic island by a factor of 20 or 30. The fundamental isolation remains. No matter how advanced technology becomes, the local group and perhaps the Virgo cluster represent the entirety of humanity's potential cosmic domain. 2,000 galaxies at most, perhaps 80 galaxies more certainly, from an observable universe containing 2 trillion galaxies. This is the final answer to questions about intergalactic civilization. Not impossibility due to technological barriers, not impossibility due to insufficient time or resources. Impossibility due to cosmological structure. The universe itself has determined what can ever be reached, and it has placed almost everything beyond reach. Scientists describe this situation as cosmic loneliness, and the term carries weight beyond metaphor. Civilizations that might exist in distant galaxies are causally separated from us. The laws of physics that govern signal propagation, spacecraft trajectories, and gravitational interaction all point to the same conclusion. We cannot send them signals that will ever arrive. We cannot receive their messages that could never depart toward us. We cannot influence their development or be influenced by theirs. Consider what this means for questions about extraterrestrial intelligence. The Fermi paradox asks why we have not detected signs of alien civilizations despite the apparent probability that they should exist throughout the cosmos. Many proposed solutions focus on the difficulty of interstellar travel, the tendency of civilizations to destroy themselves, the possibility that intelligence is rarer than statistical estimates suggest, or the hypothesis that advanced civilizations deliberately hide their presence. Cosmological expansion offers a different answer, one that operates at a more fundamental level than any of these proposals. Even if civilizations flourish throughout the universe, even if billions of intelligent species have arisen across cosmic history, even if some have developed technologies beyond our wildest imagination, expansion has separated them so thoroughly that contact between galaxies is physically impossible. The universe might teem with life. Every galaxy might harbor multiple civilizations. Intelligence might be common, even inevitable, given sufficient time and suitable conditions. None of this would make contact possible. We might share a universe with countless thinking beings while remaining forever alone. The isolation is built into the geometry of space-time itself. This isolation will only deepen across cosmic time. As dark energy continues driving, accelerating expansion, more galaxies will cross beyond the event horizon. The boundary of possible contact will shrink. Structures currently visible will fade into permanent inaccessibility. The observable universe will contract even as actual space expands beyond all measure. Future astronomers in Milky Way-Andromeda will inherit a cosmos that appears almost empty. Their telescopes will reveal perhaps a dozen galaxies within their observable volume. The cosmic web, the microwave background, the distant supernovae that revealed expansion and acceleration, all will have vanished beyond detection. As explored earlier, the universe will have erased its own history, leaving future scientists to conclude their galactic island has existed eternally in an infinite void. This temporal asymmetry creates a profound privilege for present-day observers. Humanity exists during a brief window when the universe still reveals its structure and history. We can see billions of galaxies. We can detect the cosmic microwave background. We can trace cosmic history back to the first moments after the Big Bang. This knowledge is not permanent. No, it is a temporary gift of cosmic timing that future intelligence, no matter how advanced, will never share. Some philosophers argue this represents fundamental tragedy. Consciousness has developed the ability to understand cosmic structure, only to discover that most of that structure lies beyond possible contact. We can see what we cannot have. We can comprehend distances we can never cross. Our understanding illuminates our own insignificance. But perhaps this perspective misses something important. The local group, even in permanent isolation, contains resources and possibilities beyond any current human conception. 80 galaxies harbor trillions of stars and likely quadrillions of planets. The merger of the Milky Way and Andromeda will create a stellar population rivaling the largest galaxies anywhere in the observable universe. Future civilizations, if they persist, will have access to energy and material reserves that dwarf current human resources by factors too large to meaningfully express. Consider the scale of stellar energy available within our gravitational island. Trillions of stars, each a fusion reactor producing power continuously for billions of years. The energy available defies any attempt at intuitive understanding. A civilization capable of capturing even a small fraction of this stellar output would command energy reserves that make current technology look Paleolithic. The concept of a Dyson sphere, a hypothetical structure surrounding a star to capture its full energy output, has been discussed since physicist Freeman Dyson proposed it in 1960. A civilization building Dyson spheres around even a fraction of local group stars would access energy reserves sufficient for projects we cannot currently imagine. The material resources within our cosmic island similarly exceed comprehension. Each star hosts a system of planets, asteroids, and debris containing every element on the periodic table. Heavy elements synthesized in stellar cores and distributed through supernova explosions provide raw materials for any conceivable technology. The asteroid belt of a single stellar system contains more iron than humanity has ever mined. Multiply by trillions of stellar systems across the local group. Gas giant planets contain atmospheres of hydrogen and helium that could fuel fusion reactors for billions of years. Rocky planets provide solid materials for construction. Icy moons offer water in quantities that dwarf Earth's oceans. Each stellar system represents a complete industrial base, waiting for exploitation by sufficiently advanced technology. The timescales available for utilizing these resources stretch beyond imagination. Stars will continue shining for trillions of years. Red dwarf stars, the most common stellar type comprising roughly 70% of all stars, burn their fuel so slowly that some will persist for 10 trillion years or longer. The smallest red dwarfs will continue producing energy when the universe is 1,000 times its current age. Consider what 10 trillion years means. The universe is currently 13.8 billion years old. 10 trillion years represents roughly 700 times the current cosmic age. Civilizations arising now, if they survive, will have access to stellar energy for timescales that make the entire history of the universe to date seem brief. The Big Bang will be a recent event compared to the lifespan of the longest-lived stars. Even after the last stars burn out, energy sources will remain. White dwarf stars will continue cooling for quadrillions of years, their residual heat available for extraction by sufficiently patient civilizations. Black holes will persist for timescales measured in Google years, eventually evaporating through Hawking radiation in a process that could theoretically be harnessed for energy. The universe will not become truly dark and dead for timescales that exceed current cosmic history by factors of 10 to the power of 100. Within this gravitational island, the potential for exploration and discovery remains essentially unlimited on any human timescale. The nearest stars sit 4 light-years distant. With propulsion systems that might realistically be developed within coming centuries, journeys to these neighbors might require decades or centuries. The engineering challenges are immense, but not obviously insurmountable. Human technology has progressed from wooden sailing ships to spacecraft in 5 centuries. Another 5 centuries of development might yield interstellar capability. Expansion across the entire Milky Way might require millions of years. This timescale exceeds all of human history by factors of thousands, but it does not exceed the lifespan of stars. It does not exceed the stability of stellar systems. It does not exceed the timescales on which planetary surfaces remain habitable. Civilizations that persist could eventually reach every corner of our galaxy. Reaching Andromeda before the merger brings it to us would require tens of millions of years at achievable velocities. But the merger itself will deliver Andromeda to our doorstep, combining both galaxies into a single structure where internal travel requires only galactic rather than intergalactic distances. The cosmic collision that might seem catastrophic actually simplifies long-term travel by eliminating the intergalactic gulf. These timescales exceed human lifespans by factors that seem insurmountable, but they do not exceed the timescales available to technological civilization. They do not exceed the persistence of stellar energy sources. They do not exceed the stability of planetary systems and habitable environments. What seems impossible on human scales becomes achievable on cosmic scales if civilizations can maintain continuity across the necessary timeframes. Perhaps the appropriate response to cosmic isolation is not despair, but recontextualization. The distances humans will never cross are not failures of ambition or technology. They are features of the universe itself. woven into the fabric of space and time at the most fundamental level. Cosmological expansion created these boundaries before humanity existed. Accelerating expansion is making them permanent, regardless of what choices humans make. Nothing within the laws of physics as we understand them, and likely nothing within any possible laws of physics, can overcome what expansion has already done. The boundaries exist, they are permanent, they define the absolute limits of possible reach, but within those boundaries lies more than humanity could explore in trillions of years of concerted effort. Consider the numbers once more: 80 galaxies in the local group, possibly 2,000 if Virgo remains accessible. Trillions of stars across these galaxies, quadrillions of planets orbiting those stars, each planet a unique world with its own geology, chemistry, and history. Each stellar system a new frontier for exploration and discovery. A civilization that thoroughly explored just one galaxy would require millions of years. A civilization that explored the entire local group would require billions of years. A civilization that catalogued every planet, studied every star, mapped every structure within our gravitational island would still be working when the last red dwarfs finally exhaust their fuel 10 trillion years from now. The boundaries constrain us. They are real and permanent, but the domain within those boundaries exceeds any meaningful definition of limited. By any human standard, by any standard a civilization might achieve across billions of years of development, the local group provides effectively infinite scope for growth, exploration, and discovery. This brings us back to the final constraint that defines human cosmic existence. The constraint that no amount of progress can circumvent, the constraint that represents not a problem to be solved, but a reality to be understood. The cosmic event horizon is absolute. Distant galaxies have already crossed beyond possible contact. More galaxies cross that threshold every moment. The universe we can never reach grows larger, while the universe we can ever explore shrinks. This process will continue until only gravitationally bound islands remain, separated by voids too vast for any signal to cross. But within those islands, existence continues. For life, for intelligence, for meaning, persist across cosmic time. The isolation is real. What remains within reach is also real. Humanity exists on one small planet, orbiting one average star in one spiral arm of one galaxy, among 80 in a gravitational island isolated within an accelerating cosmos. Our existence spans the tiniest fraction of cosmic time. Our influence extends across the smallest portion of cosmic space. By any cosmic measure, we are vanishingly small, breathtakingly brief, utterly insignificant against the scale of what exists. Yet, within this infinitesimal domain, consciousness has emerged. Awareness has developed. Minds have formed that can contemplate scales far beyond their origins. We can calculate distances we can never travel. We can understand boundaries we can never cross. We can measure the expansion rate of space itself and project its consequences across billions of years. The observable universe reveals itself to human inquiry despite our cosmic insignificance. We see galaxies beyond count. We measure cosmic structure across billions of light years. We trace the history of the universe back to its earliest moments, reconstructing conditions that prevailed when the cosmos was younger than Earth is now. All of this knowledge exists within minds that occupy a vanishingly small portion of cosmic reality. We exist during a brief window of cosmic history when the universe still reveals its structure. Distant galaxies remain visible. Expansion remains measurable. This window will close. Future intelligence may persist for trillions of years in a cosmos that appears almost empty, never knowing what we can still see, never reaching what has already passed beyond reach. Perhaps this is remarkable enough. The light from distant galaxies continues arriving, carrying messages from regions that have already departed from our cosmic neighborhood. We glimpse the unreachable. We observe the forever inaccessible. We understand what lies permanently beyond our grasp. The universe stretches beyond all possible contact. The boundaries are permanent. The isolation is complete. 97% of everything we can observe lies forever beyond human reach. But within the 3% that remains, within the gravitational island, where expansion cannot overcome attraction, possibilities extend beyond any current imagination. Trillions of stars will burn for trillions of years. Quadrillions of worlds await exploration. Energy reserves capable of powering civilization for cosmic timescales sit within gravitational reach. The boundaries exist, they are permanent, and within them lies more than humanity could explore across the entire remaining lifetime of stars. Cosmological expansion represents the ultimate barrier to human cosmic ambition. It is not a wall to be broken. It is not a distance to be overcome through cleverness or technology. It is the continuous creation of separation itself, woven into the structure of reality at levels we are only beginning to understand. The universe is not waiting for sufficiently advanced technology. It has already determined what can ever be reached. Space expands faster than anything can travel through it. The fabric of reality creates distance faster than any journey can close it. This is not an engineering problem, awaiting a solution. This is the fundamental nature of the cosmos we inhabit. The distance humans will never cross now stretches across 97% of everything visible in our telescopes. Trillions of galaxies recede beyond the horizon. Countless stars fade into permanent inaccessibility. Unimaginable worlds slip beyond any possible contact. And yet, within the boundaries that expansion has set, one small species on one small world has developed the ability to comprehend cosmic structure itself, to see across billions of light years through instruments of our own devising, to understand accelerating expansion through mathematics of our own creation, to calculate the limits of possible reach and know exactly what lies beyond. We have mapped our cosmic prison with precision that earlier generations could not have imagined. We understand why the walls exist and what makes them permanent. We can calculate exactly which galaxies remain accessible and which have passed beyond reach forever. This understanding changes nothing about the physical boundaries, but it reveals something profound about conscious beings and their relationship to the cosmos they inhabit. We are small beyond measure. We are brief beyond reckoning. We are isolated beyond crossing. And we know it. We comprehend it. We have calculated it and verified it and understood it in ways that no other known process in the universe can match. The universe expands in silence. Galaxies recede without awareness. Stars burn without knowledge of other stars. Planets form and dissolve without comprehension of their place in cosmic structure. Physical processes unfold according to mathematical laws, but those laws contain no provision for understanding themselves. Then consciousness arose. Somewhere in this vast cosmos, on at least one small world orbiting at least one average star, matter organized itself into patterns capable of contemplating the patterns. Minds emerged that could ask questions the universe itself cannot pose. What is the universe? How did it begin? How will it end? What are the limits of possible reach? We are the universe knowing itself. We are matter comprehending matter. We are physical processes that have gained the capacity to understand physical processes. This may be common. Life may flourish throughout the cosmos. Intelligence may arise on billions of worlds, or we may be vanishingly rare. A singular emergence in an otherwise unconscious expanse. We do not yet know. The distance humans will never cross defines the boundary of cosmic existence. Expansion set these limits before life arose on Earth. Acceleration is making them permanent as we watch. Nothing we do can change them. Nothing we achieve can overcome them. They are woven into the structure of reality itself. But what we do within those boundaries, across the trillions of years that stars will continue shining, within the galaxies that gravity holds together against expansion, remains entirely up to us. The universe has spoken its limits. Clearly, precisely, mathematically. The cosmic event horizon marks the absolute edge of possible reach. Beyond it lies most of everything that exists. Within it lies more than any civilization could explore across cosmic time. The boundaries are permanent, the isolation is complete, the distances are forever, and within those distances, one small species has begun to write its story among the stars. The rest is ours to determine,